So in this short section, we're going to look at the formation of bands themselves in terms of the bringing together of atoms. So this is from a slightly different perspective than the Kronig-Penny model that we just did. This is from an atomic bonding perspective. So if we start with two different atoms separated by an infinite distance, they'll each have their isolated wave functions. So if we imagine that these are hydrogen atoms, and these are the 1s wave functions. So now we're going to imagine what happens as we bring these together. So as I drew in the last video, you can put these wave functions together in two different ways, one where they're connected by a plus and one where they're connected by a minus. And I'll just draw this one right on top of it. Now the energies of these two are slightly different. So we can represent that by what's called a bonding diagram that just shows the energy levels. So the energies of these two 1s orbitals are here and here for the two separated atoms. And then when we bring them together, what we'll see is that the resulting energies of these two wave functions go slightly up or slightly down. So if we have in a hydrogen atom one electron in each atom, when they come together to form this molecule, the two electrons will go into this lowest available energy, the E+ solution, and occupy it. So we have here two available slots for an electron because of the spin in the atom on the left, and two in the atom on the right. And when we bring them together, we have two available spots filled up with two electrons. And then in the upper E- orbital, or what might be called an antibonding orbital in chemistry, we also have two spots, but they're both empty. So now we're going to look at what happens if instead of having just two atoms, we have a vast number of atoms, millions or billions of atoms. We can't draw the same simple diagram with the energy levels splitting, but we can represent sort of what happens in aggregate. So we're going to draw a schematic diagram now that represents what happens when you have a chain of atoms, n atoms long, and they're all separated by some distance d. And we're going to bring this chain of atoms together from infinite spacing down to d. So for d equals infinity, all of these 1s energies have the same energy. But as we bring them together, their orbitals start to split and mix, and we form a band of solutions. And out here we have n atoms. We have n 1s orbitals. And we have 2n spots for electrons because of spin. We can put one as up or one as down. And we actually only have n electrons if we consider these to be hydrogen atoms. Now, more complicated things happen if instead of restricting ourselves to hydrogen atoms, let's consider what would happen if we had a more complicated atom like silicon. So I'm going to change these countings. So the same sort of phenomena will happen, but instead we'll have the s orbitals and p orbitals involved. We'll have the same sorts of splitting, but the counting becomes a little more. So again, if we have n atoms, we're going to have n s orbitals and n p orbitals for each of the three directions. So we actually end up with 3 times n p orbitals. Each of these orbitals can hold 2 electrons at most. So what we have to remember is that in the silicon crystal, the spacing between atoms is fixed because of the lattice constant of the crystal. So schematically, at least, we can see that we have a band of allowed states, a gap between which no solutions to the Schrodinger equation can exist, and then another band of states here. So let's look at the counting of orbitals and electrons for this hypothetical chain of silicon atoms. And because we can't quite draw all of them, I'll go back to the sort of more traditional picture of the conduction band, the valence band, and the band gap. So if we have n silicon atoms, we'll have 4n orbitals. And each of these orbitals can hold a up and a down electron, spin up or spin down. So this is the total number of orbitals. When we split these into the conduction and valence band, there will be 2n orbitals here and 2n here. Now each silicon atom brings with it 4 electrons. So we could draw the silicon atom looking like this in real space. So we take these 4n electrons, and we have to populate them into the available orbitals, filling them in terms of energy. So we start putting them in spin up, spin down, spin up, spin down, so on and so forth. And if we look at the numbers here, there's two choices for spin times 2n orbitals, and that gives us actually 4n electrons, which completely are going to fill this lower band. So they'll fill exactly to the top of the band, no more, no less. So what that means is that this entire band of states, or this entire set of orbitals, is completely full of electrons. And then there's an energy gap, typically for silicon of about 1.1 electron volts, before you can reach the next available orbital. And this means that silicon should be considered really more like an insulator. We call it a semiconductor just because the band gap has a certain value of about 1 electron volt, whereas traditional insulators might have between 5 and 12 electron volt band gaps. But critically, what it means is that if all of these orbitals are actually completely full, it cannot conduct electricity at 0 Kelvin. It means that you have to actually excite electrons somehow across this band gap, or to dope the silicon to add electrons into the conduction band for N-type conduction, or to subtract electrons out of this valence band for so-called P-type conduction by holes. So in this little segment, we've looked at how we can take a collection of silicon atoms and put them together, and by doing the detailed counting, we can figure out whether or not this silicon solid should conduct electricity in the absence of thermal excitations up to the conduction band or of extrinsic doping. So now let's quickly look at these types of band diagrams for insulators, semiconductors, and metals right next to each other. So again, we'll draw these little rectangles. So here's our representation of silicon, and we have the conduction band, valence band. And for an insulator, which I alluded to a moment ago, the bands are going to look exactly the same, but the value of the band gap is much, much larger. And what this means effectively is that there's no way for thermal excitations to jump electrons across this energy gap, except at temperatures of thousands of degrees Celsius. So they're no good for making traditional electronics. So semiconductors are usually defined as having band gaps in the range of, let's say, between half an electron volt or even a smaller fraction of an electron volt up to 3 or 4 electron volts. Insulators have much bigger band gaps, but still at 0 Kelvin, the valence band is completely full of electrons, as it is for a semiconductor. Now, metals are just slightly different. They might have the same 2 bands separated by a gap, but the number of electrons that each atom brings to this solid is different. And the numbers work out such that, let's say the entire band 1 here is full of electrons, but the next band is only partially full, up to some value that we call the Fermi energy. So for a metal, the next available state is separated by a tiny infinitesimal delta energy from the highest occupied state. And that means for even the smallest electric field or voltage that you put on a metal, the electrons can start to conduct electricity. In this section then, we've gone from a simple picture of atomic bonding, bringing together chains of atoms, all the way to representations of the band structure for the 3 general classes of materials: insulators, metals, and semiconductors. And it's these classes of materials that we'll use to build up our semiconductor devices.